recording. All right. Okay, so we may not be able to finish all of the shading slides today, but at least we will just have a starting point of how we can implement shading. I will quickly go over the three components that we are going to put into our color computation. The basic illumination model, the first component, which is composed of three components on itself. The shadow and reflection. Okay, and I remember the first time I implemented my own ray tracer was about 5-6 years ago when I was teaching this course. Before then I have never implemented ray tracing before, and while I was implementing the reflection part, that was the most difficult part for me. Reflection following the rays recursively. That's the recursive part of the ray tracing, and it was also the first time I had to implement a mutual recursive program. There was two functions, mutually recursive functions, that was needed. I mean, I teach. I mean, okay, this is called mutual recursion. We teach it with toy examples. But this was the first time in my life that I had to actually wrote a recursive function, which was mutually recursive between two functions. But probably it's just a design artifact that I had. Probably you would not need such a thing if in your implementation. But if you need something like this, I mean, don't get surprised. That's the most difficult part in your implementation will be that recursive part in which we are going to compute reflections. All right, so let's continue. Oh, by the way, am I recording? Yeah, I'm recording this. All right, so we have talked about the RGB model. Our materials are going to be represented with three components, RGB. Also, the power of the light or the color of the light will also be represented by three components, RGB. Or we sometimes call this intensity of the light. Okay, so the intensity of the light, let me put it a little bit this way. Okay, so the intensity of the light, you're going to have, it will vary from 0 to infinity, and how much red light the light source emits. This intensity, we can have different models for that. We already know that the colors that we will be putting into our image, into our ppm image, we will represent them as integers between 0 and 255, right? If they're between 0 and 255, we don't want this power to be, for example, thousands. You need to be really careful about when you are designing your what should the light intensity be, what should the reflectance coefficient be. You know, while you're determining those things, you should think about how bright you want your scene to be, how dark you want your scene to be. So this intensity really determines the brightness, the amount of light you have in your scene. Another thing is, which we'll see that later, this light intensity in real life actually diminishes as the light moves from the light source to a distant location. Okay, this is called attenuation. I'm writing also in chat box, attenuation. So attenuation means the decreasing of the light power as it moves away from its source. So which means that if an object is far away, it's going to get less power comparing to an object that is closer to the light source. And we may, if we are going to implement attenuation with some kind of, for example, quadratic, if it decreases inversely proportional to the distance, it may drop quickly as you move, so you may give large power values. Another thing about the light computations, I mean the color computations they will always be additive, meaning that the color for a pixel when we compute it, if there are multiple light sources, their effects on that pixel will be additive. We will sum all the contributions from, for example, we will see in the simple illumination model, we will have the diffuse component, the specular component, ambient component. We will just add them to the pixel's color value. And at some point, we may get values larger than 255, which means that that pixel at that point, that color component, saturated. This also happens in real cameras. When too much photons, when you have a very high exposure, you just get a completely white picture, white photo, because the whitest you can get, because the light rays just accumulate there and it saturates. So this also happens it will happen in our model. So when the value, since everything is additive, we will not have any negative contributions. Color cannot be, or the reflectance, the interaction with the power of the light with reflectance can never be negative. The smallest it can be is 0, no color at all, and 0 is going to give us black. Okay, there is no negative white. I mean, there is no negative color values. The smallest we will have is going to be black, but everything will be additive. So we need to be careful when things go below 255. We should just clamp the largest value to 255. Clamping is basically saying that if the value gets larger than 255, I will just treat it as if it's 255. All right, now let's get back to the slides. So power, intensity, radiance, irradiance. So again, here are the details of the interaction between the light source and the material, and I'm going to skip those things. I mean, we are going to have a very simple model which uses vector algebra to compute the radiance on a surface, but here the power is the light source's power, and you can, these are the real physics of what happens with a light source. So there is this when the light source actually is not omnidirectional, as we will assume a point light source in our scenes, they will emit light in all 360 degrees around itself. But in reality, in a solid angle, for example, the light rays, they disperse. And therefore, the amount of the light that is given here is given by the derivative of this power and the solid angle. So the larger the angle, the power is going to be dispersed in that area. Okay, so this steradians 3D version of an angle is used here. So these are really complicated light intensity computations, which we will not use in our models. That's why I'm going to quickly skip them. The solid angle, we are not going to do a global illumination. We will not try to compute the amount of light that comes to an entire area along a sphere. But this is, I mean, if you're going to go into more details in later, if you're going to, for example, take the course Advanced Ray Tracing or Advanced Graphics, Computer Graphics, you may need these things. Okay, so that's why I'm skipping these quickly. All these physics, solid angle, flux, I don't know them myself. All right, I don't use them in my ray tracer that I have showed you. The model that we're going to be using is very simple, but this is the actual physics of what is going on with the surface, how the light interacts with the surface. All right, but here, something that from this physics, we are going to derive the simple model. Actually, those simple models come from the actual physics. It basically says that. So this first one, this radiance tells that if the light rays come to a surface at a direct angle, they are reflected most. If the light rays come to a surface with some angle, the amount of light that is reflected off the surface is actually proportional to the cosine of the angle that light rays make with the surface normal. So this is going to be our first observation that we will use in our ray tracing algorithm. Yeah, our goal will be to compute radiance along each viewing ray. So we will not, the steradians, the area, we will not use them because our rays really are one-dimensional objects. Their area, they don't occupy a certain area. So they will not have per unit area. So irradiance, these things, they're really the actual physics of things which we will not use. So I'm skipping these. Okay. So the important thing here is the cosine. You are going to see that. The inverse square law, also the irradiance emitted by a point light source is reduced by the square of the distance from the source. So as you move away from the, so this is about light attenuation. We can also have this as modeled simply if you compute the distance from the surface point to the light source, let's call it D, for example, you can decrease the light intensity by 1 over d square every time you are computing the intensity for a point. So this will be called attenuation. All right, so this is the cosine law states that a surface can receive or emit radiation only in proportion to its area projected in the direction of the light. So this, again, this talks about aerial intensities, but we will be really in the ray tracing algorithm that we will implement, we will be interested in surface points. We will not be talking about areas, but the model that we are going to use is going to come from this cosine, and it will simply be this. So actually I can just, instead of going over these slides, I can just tell you quickly our simple elimination model. So let me also skip this one. This rendering equation also, it's a continuous equation over all the area. It's very complicated in the sense, but its main basic form will remain the same. So this one says that the light that is radiated at a given surface point with a given material is simply be this, which tells me that the emitted light, if that surface point itself is a light source on itself, it will emit some light. Emitted light plus the integral over the area of that surface. So our area, we will not have any area, we will have the surface point, a singular point here, and this function is for each light source, we are going to look at the cosine of the angle. So we will not be using this. Render's equation is very complex, involves continuous integration over a surface. We will not be using this. Okay, so emitted, yeah, this is reflectance function, incoming radiance, integration over hemisphere. And this is the differential solid angle. So after describing all these things, we will just basically say that this is too costly to evaluate. For each surface point, we need to integrate against everything. So simplification, we will exclude all directions except the light sources, add an ambient term to simulate what was excluded. Now, let me actually, at this point, let me just tell you about our simple model here on GIMP. Okay, so the color along a surface, we will have it computed in 3 components: ambient, diffuse, and specular. And I will just illustrate it on a sphere, okay, each of these components. So if I want to compute the color of a sphere, so imagine this is my ray, and it hits a point on a sphere. Okay, my goal is, so I have a sphere here. My goal is to compute, so this is the point P my ray hits. My goal is to compute the color of this point P. This is the ray that's coming out of a pixel. Okay, so this is my ray. My goal is, so the color of that point P will be computed in our simple, this is also called basic illumination model, is going to be composed by adding 3 colors together. The ambient component, and for each light source. So this diffuse and specular component actually is an additive term which means that for each light, okay, for every light I, diffuse component from that light I and specular component from that light I. So if you have multiple light sources, each of them will contribute a diffuse and specular component, okay? If you have only one light source, you're just adding these three things. So I'm going to describe what this diffuse and specular component are, but ambient component is something independent of any light sources in the scene. It will be used to model default existing light everywhere in the environment, independent of where the lights sources are. So it's like the room is illuminated by default with this ambient amount. You can think about the ambient light source like that. Usually the ambient intensity is given as parameter to you. The ambient light's power source will be given to you. For example, it may be 50, 50, 50, or let's make it 20, 20, 20. Okay, so this may be a, as you can see, low intensity light source. This is the power of the ambient light, which will be given to us in our scene description file as input. Okay, so depending, this ambient light being white does not mean that the ambient component of every object is going to be white. What we do is our object has a reflectance coefficient. Let's call it K. Okay, the reflectance coefficient will indicate the color of the object to us. For example, it will be, let's have a red sphere. Okay, in this red sphere, I'm going to have 1, 0, 0. So these may be my reflectance coefficient. So the ambient component of this point's color, the first thing that I'm going to be adding, will actually be equal to, the color that I'm adding is going to be equal to 20, 0, 0. Okay? Which means that if this point is in shadow, if there is no diffuse or specular component, the color that I'm going to be putting on this pixel is going to be 2000, some dark red. Okay, so if it's in shadow, it will not be pitch black. It will be dark red. It's not 000 because of this ambient component. Its ambient color is this. And I'm going to add to that the diffuse and specular components. Let's first talk about the diffuse component. What is diffuse component? Diffuse component is the component to model the roughness, non-smoothness of the surfaces. If we have, so what you have seen in physics in high school is something like this, right? I mean, if a light ray comes to a surface, it's reflected with the same angle. If this is alpha, this is also alpha. Or, I mean, you may talk about it also in terms of surface normal. If this is beta, then this is also beta. Okay, so the incoming light ray is reflected in the same direction coming. So angle of incidence is the same of angle of reflection. So this is actually true only for very smooth surfaces. If our plane here is infinitely smooth, that happens. Such a thing happens like in surfaces like mirrors. But in reality, I'm going to undo this. In reality, our surfaces, if you have a microscope and if you look at the surface of some matte object, the surface actually is all jagged like this, okay? It's not smooth, okay? Look at the surface. It's going to appear like this. Now, when light ray comes here, I mean, just, we were not considering consider as it comes to an area. In that area, lots of non-smoothness occurs. Therefore, based on the normal vectors on these non-smooth parts of the surface are all over the place, which means that our light rays are going to be reflected in every direction. Okay? So this is what this diffuse component is about. We are not interested in the light that is reflected in a certain direction, but the light, for example, if I have a light source here, okay, if this is my light source, the light hits this point P, okay, it is reflected in every direction equally. That's what the diffuse component is about. Okay, diffuse component does not think the light rays that is coming here based on the material properties is going to reflect it in every direction equally. That's what diffuse means. It's diffuse. The light is diffused in every direction. But what is important is how much light is going to be diffused. What is the intensity of the light that is diffused? For example, if consider this another point, P2, the light rays that are hitting here are going to be more stronger, more intense compared to light rays that are hitting here. Okay, because consider it like this. If there's a light source that is hitting directly on a surface, most of the light rays can be reflected. But if there is the light rays coming like this, and if your surface is like this, not many light rays are going to be reflected, less rays. Or, I mean, at the extreme case, imagine if your surface was like this. Its normal vector is 90 degrees to the incoming light direction. In that case, nothing can be reflected, right? I mean, light rays simply graze through, I mean, they just skim through this surface. They cannot be reflected off the surface, okay? Now, here, in the diffuse component, we are just going to be doing basically this. Whatever the normal vector of the surface, okay, let's call this surface point. Okay, normal of the surface at this point. That's the more correct way to do. So if the normal of the normal vector along the surface point is n2, and if this is the light rays incoming direction to this point P, if this is angle alpha, what basically we do is the diffuse component is equal to whatever the diffuse power of the light is times the reflectance coefficient times cosine alpha. Okay, it's this simple. And alpha here, so how do I compute this cosine alpha? Any ideas? The dot product, right? If you basically take the dot product of your normal vector with the light vector here, if these are normalized, if their lengths are 1, if they are unit vectors, if they are normalized vectors, their dot product immediately will give me cosine alpha. Okay, so this is what the diffuse component is. Now, you may ask, cosine alpha ranges between -1 and 1, right? What if cosine alpha turns out to be -0.5? This means that I'm going to have a negative. So it's minus 0. It could be cosine alpha, could be -0.5. In that case, the diffuse component will be negative. I just told you that it cannot be negative. In such a case, if it's negative, it means that our surface, for example, the surface is looking this way, and the light direction is coming this way. Okay, if the light is coming this way while surface is looking this way, as you can see, the angle between them is greater than 90 degrees. In that case, cosine alpha is going to be negative. In that case, actually, my light rays do not hit the surface at all. So what I will need to check is that only if this cosine alpha is greater than 0, I will take into greater than or equal to 0. If it's equal to 0, the color will be 0 anyways, so there's no need to consider it. If the cosine alpha is greater than 0, which means that the light rays are coming either directly or at most at an angle, so the light rays are coming this way. If it's parallel, cosine alpha, the light rays are parallel to the surface, which means that it's 90 degrees to the surface normal. So this is the case where cosine alpha is 0. This is the case where cosine alpha is 1. All right, so the dot product of these two things. The normal vector, by the way, the cosine alpha, I showed you as two opposite vectors. Actually, what I will have is, I will have the vector I will define the vector from the point to the light source. Therefore, they will be in the same direction like this. Okay, but anyway, you get the idea. So the diffuse component is just computed by using the surface normal and dot producting with from point to light vector. So this is basically the diffuse component. All right. Let me ask the kids to be quiet. Çocuklar sessiz olabilir misiniz biraz? Dersteyim. All right. So these are the two components. The last component, specular component, actually is used to model mirror-like reflection, mirror-like bouncing of the light. It's actually used to model smooth surfaces. So the last component, so the color was ambient, diffuse, and specular. And if we just add ambient and diffuse, this is what we get. So you have actually seen, if you have looked at our ray tracer, let's just take a look at the code now. What we have did earlier, let me uncomment these parts. Okay, this one. Where did the comment start? Did it automatically? Oh, I think it's somewhere here. Where is? Oh, it's right here. So it was weird. I wasn't seeing the left part of this. So okay. So if you look at this, oh, I see. Notepad and VI somehow treat tabs differently. So these are the additional tabs I added in Notepad++. It was open in Notepad++. Now I'm editing it in VI. So that was the main difference for the indentation difference we were seeing. So look at this. So the code you see here right now, this code is implementing the first two components of the basic illumination model, ambient and diffuse. The ambient is actually implemented simply by this 3 lines of code. I just added 0.05. Actually, the way the implementation is done in this code is the reflectance coefficients and the light intensity are not defined as they are on the slides. The reflectance coefficients here are not between 0 and 1. They are actually between 0 and 255. So they're like their roles are reversed. Here, the color of the object is between 0 and 255, and the intensity of the light is between 0 and 1. So it's not as correct implementation. So, I mean, if you want to use part of this code that I shared with you, be really careful about this, all right? So this is implementing it in a different way. But if you look at this, so the ambient color says that just add a small amount of RGB so that things, the surface points that do not see the light directly, they should not appear pitch black. Okay, so let's actually, if you comment these out, you're going to see the effect of ambient light. So let me comment them out and let me compile and run it again. All right, so if you look at the image, we'll see that now the image contains just the diffuse component. Okay, with just a single diffuse component, it looks like this. You see the parts where the light is not reflected, where cosine alpha of the normal point. So light is somewhere here. So these are the surface normal. As the light vector and the surface normal, the cosine alpha, if it's less than 0, it becomes black, pure black like this. All right, we cannot distinguish from the background. Now, I'm going to add to this color the ambient component, and you'll see the effect. When we add the ambient component, and actually let's have the ambient component a little bit larger, 0.1. So when I do that, let me compile and run it again. All right, now let's see the figure again. You see what happened with the ambient component? The bottom parts of the sphere is no longer black. Okay, it's some dark yellowish color. This is what the ambient component is about. It adds some default color to parts of the scene that cannot receive any light. All right, and it doesn't have any specular component. This, what we are seeing here, is diffuse, which makes some matte material. Light is reflected on every direction, so we cannot have brightness or shininess. Shininess cannot be represented with this two components only. The third component that I'm going to show you is called the specular component, and it's used to model this shininess. I think I have that implemented. Oh, by the way, if you take a look at the code again, how diffuse component is implemented, look at this. We have these vectors, normal vector on this point. So this vector P is the, right now all I have is, at this point, after I find the closest object, the only two things that I record are the parameter T, at which point on the ray I intersect with this point, and the ID of the sphere that I'm intersecting. It's sphere K is being intersected with this ray. So first of all, I need to find the coordinate of the point on the sphere. Then I need to form these normal and to light vectors to compute this diffuse coefficient. Okay, so if you look at this, the point P simply, look at this, what do? We just plug in this T into the ray equation, starting with, this is the start of the ray, this is the direction of the ray, the B component is the direction of the ray. So this is basically just plugging in T min into the ray equation to find the point P on the sphere. And then we find the normal vector by just subtracting this P. I mean, the way I implemented these are really cumbersome. I mean, I could just have implemented, I mean, look at this. What I do is I multiply the sphere's center with -1 so that it becomes a negative vector. And I add, so it's basically saying P minus center of the sphere. It becomes the normal vector at that point. And I normalize that normal vector so that it has length 1. And this is the to light vector. The same thing I do. I have the light position. I just simply say that light position minus P becomes my to light vector. I normalize that too. So they become both unit vectors. Then simply I take the dot product of the two vectors, which gives me the cosine alpha. So this diffuse component you see here, this diffuse variable, is nothing but only cosine alpha of these two vectors. If it's less than 0, I set it to 0. So to just avoid negative values. And then what I simply do is, whatever the color of the object is, I take my color light intensity power like 1, and whatever the reflectance coefficient is, I multiply it with colors intensity, light intensity, which, as I said, is like 1, and I multiply it with this cosine alpha, which is the dot product between N and L. That becomes the diffuse component. So it's that simple. With just two things, our bad scene, which was just same color spheres, turned into something like this. Okay, they became three-dimensional. Now, the last component, the specular component, as I said, is for shininess. And let me also talk about that in a new slide here. So the diffuse component, I mean the specular component, is like this. Let's have the same ray again, and on a sphere. Okay, now I have the light ray. Okay. So the light is coming to this point. If this was a mirror-like surface, the light was going to be reflected off in a direction that we have seen earlier. The angle of incidence, whatever it is, alpha, it will be equal to angle of reflection. Okay? So this is, if it was like a mirror, imagine, and this is our eye. This is our ray where we are looking at this point P. Okay, so this is alpha, this is alpha. So imagine this is like a mirror, and somebody is trying to shine some light on your eye. Okay, so if this is the point, if the eye was here, we would see a really bright light, right? I mean, if this was like a mirror, it was really pure like a mirror, and this is really like a point light source, this would be the only point where we will see the reflected light clearly and very brightly. Now, here, not all the surfaces are like mirrors. They are shiny, but not exactly like pure mirrors. So what we will do is, we will actually say that around this reflected ray, if you're around this reflected ray in certain amount, if the camera is around here, you will still be able to see the reflected light, but with some decreased amount. I mean, if the eye was directly along this line, it will see the reflected light in full intensity. But if it moves away here, so what we'll actually do is, let's call this ray the reflected ray. It's the reflected ray, and this is the to light vector from the point to the light vector. We are going to use the normal and light vectors together to find this reflected ray. Now, what we will do is basically simply, this is my, let's call this view vector from the camera to the point. I'm going to now take the cosine of the angle, cosine alpha, between the view vector and the r vector. If you look at this, if view vector and r vector were the same, if they were just along each other, exactly on top of each other, I would see the reflected light fully, right? So hence, if you just take again, this view vector is 2 view like this in the other direction, in the reverse direction. So it's actually, where did I put this? So anyway, so the direction is 2 view vector like this. And I'm going to take the cosine of the angle between these two vectors, and that will be my specular component. And in order to, so the specular component is like this. Specular component is going to be equal to the light intensity times reflectance coefficient and the cosine of the other angle. Let's call this other angle beta this time. Okay, beta is the angle between the view vector and the reflected vector. It will be something like this. All right. In order to, I mean, this is the simple way, but actually what we will do is we will take some power of this. Let's call it specular coefficient. Why do we take the power of cosine beta? To basically model more shiny surfaces. I mean, if I just take cosine beta, irregardless of the surface, based on the angles so we will be able to do this shiny spot in a 90 degree, I mean, actually it's like this. If this is R, this is the view vector, and this is the other view vector. So in a range like this, we will be able to, everybody along this range will be able to see this reflected ray, but with some decreasing shininess as we move along from the ray. If we want this shiny spot, so we will have a big shiny spot here actually. If we want this shininess to just be limited to a certain angle around the reflected ray, if we want this shininess to drop quickly as we move away from this reflected ray, one thing we may do is we may take the power of this number to some integer exponent. I mean, for example, if ns is 100, or let's just, for example, if it's 10, if this specular exponent is 10, what happens? Cosine beta here is a value between 0 and 1. If you take a power of a number between 0 and 1, what happens? It will become smaller, right? So it will only be able to stay large when cosine beta is closer to 1. So the effect, so this is the specular exponent basically. What we will do is we will compute the view ray, we will compute the reflected ray by using again the normal and to light vectors. And this specular exponent will be a property of the material telling us how shiny it is. Okay, so at this point I can actually go to the slides and show you what kind of effect this shininess have. And after that I'm going to finish. So this basic illumination model is a very important component of the ray tracing shading. And for shadows, we already talked about shadows briefly on Monday class. We just compute again the ray from the point to the light, the same L vector. So this vector, we will be using it a lot. If we come back to this one here, this ray from the point to the light that I drove here, from point to the light, this ray, we will be using this ray a lot. We will be using it for diffuse component, specular component, and finally, we will also be using for computation of shadows. That ray, we will intersect with other objects to see whether light rays are occluded or interrupted by some other object between the light source and that point. That's how we do the shadows. So this is the surface normals. The sphere surface normal is simply P minus C. We have talked about that. The surface normal of a triangle simply is the cross product of any two edges. And the shading model we will use will simply be, I'm going to show you the simple shading model. It will be composed of diffuse, ambient, and specular component. We have talked about the diffuse component, the angle to light, and the normal vector. This is called theta here. The cosine theta will be multiplied with the reflectance coefficient to find the diffuse component. Okay, so this is how a diffuse shading gives us the results. We have seen that in our own example. Our spheres were not gray, but if they were gray, we would get something like this. Ambient shading, as I said, is the default lighting in the environment. Regardless of the light sources, we just multiply the ambient intensity with the reflectance coefficient to get the ambient part. And the difference here is that with diffuse only, we get black parts here. With edit ambient, we have dark gray parts, not black. Now, specular shading, sometimes called Blin-Fon shading, the difference, by the way, if you take a look at the diffuse and ambient components, camera position, the I vector is really irrelevant when computing the diffuse and ambient components of the position point on a surface. So they are view independent. But if you look at specular shading, this is the first time we took into account the view vector, the ray, the vector from along the ray. Okay, therefore it's view dependent. As you move the camera around, the shininess is going to change for a specific point. So as you can see, what we do is if this is the normal vector along the surface, if this is the to light vector, Wi here is the to light vector, this is the normal vector. We will actually be looking at the cosine of the angle between the reflected ray. This W0 is the reflected ray. Sorry, W0 is to the view, I think. The reflected one is going to be somewhere here. So the method that is described on this slide is a little bit different, and it will give us some different results than the method that I show you. The method that I show you here actually is the correct method. All right, so let me show you here. So the angle between the view vector and the reflected ray is actually, that's the cosine beta is used in the original method. But if you look at the other vectors in which, let me also get a new slide, and after that I'm going to finish today's lecture. So now I'm going to describe what is on the slide. So look at the normal vector. So this is the normal vector, this is the incoming light vector, this is the to light vector, this is L, P, this is N. The light, this is R, right? The incoming light is going to be reflected in this direction. And imagine we are viewing the scene from here. This is where the eye is, and this is our view vector. Okay. Now, what this one actually computes it computes the half vector between the view vector. Look at the view vector and the if the reflected light, this is the perfect reflected light. If you look at the normal vector, it's exactly in between the normal vector is in between the light direction and the reflected direction, right? I mean, this is alpha. This one here is also alpha. Okay, so the normal is in between light and R. Now, what we do is we compute the half vector between the V and the L. Okay, so this V vector and L vector, let's compute the half vector in between them. Let's call it H. If this H and N are exactly on top of each other, what does it mean? It means that V is exactly the same as R, right? I mean, so I computed a half vector between V and L. This is H. If H and N are on top of each other, then it should be V is equal to R. So what basically we do is we compute the half vector between V and L in this method, and we look at the cosine of the angle between this half vector and the normal vector. So it's just a variation of what I have shown you earlier, but they establish basically the same thing. And the angle between this normal vector and the half vector determines shininess. All right, and we multiply it with this cosine alpha, and here the exponent is the Phong exponent. I just want to finish with different exponents. When we add the specular component, we will see a bright, shiny spot like this. This is the addition. So as you can see, this is a diffuse and ambient. No, it doesn't appear shiny. With the specular exponent, we get our spheres that appear shiny. And this is how Phong exponent changes the appearance of shiny appearance of an object. Okay, so I'm going to stop for today. Putting it all together, we have the basic elimination model, which is one of the components. We have seen one of the components of the shading model, the basic shading. The other two components will be shadows and reflections. With that, we are going to conclude the ray tracing algorithm altogether. So the remaining things are, as I said, shadow and reflections, which I'm going to talk about on Monday. All right, so that's it from me for today. If you have any questions, you can ask, or you can always send me an email later if you watch the video offline. You can send your questions to me by email if there's any part that you didn't understand. Okay, have a nice day, everyone. See you all on Monday. Bye-bye. I will stop sharing this. Bye. See you.